Let me just take a brief introduction of today's meeting. Hi everyone, welcome to our 22nd SIGCOMM Reading Group. My name is Su, and I'm an assistant professor at Xiamen University. Today I will host this meeting on Professor Xiang's behalf. In past sessions, we have talked about some really great work from SIGCOMM, such as high-performance packet classification frameworks and enhancing RDMA reliability for lossy network. So today we are very happy to dive into an important and interesting topic, LLM training optimization, with a special perspective of multimodal natural language models. Yeah, so we will be looking at a great paper titled DistTrain, addressing model and data heterogeneity with disaggregated training for multimodal natural language models, which was published in SIGCOMM this year. Yeah, so this paper discusses it discusses the new challenges of today's training systems for multimodal natural language models, especially in terms of the heterogeneity in both the model and training data. So and it also presents an efficient framework to solve these two challenges. So I think both the academia and industry can learn a lot from this work. So usually our meeting is also live streamed on other platforms like Tencent Meeting and Bilibili. So we just recorded this meeting. So everyone can take a review for today's meeting. We will begin with a 30-minute presentation of the paper, followed by another 30-minute discussion with the authors. So today we are very happy to welcome Xiangrui Yang from the University of Hong Kong, who will be presenting this paper. In addition, we are honored to have the first author of this paper, Zili Zhang from Peking University, here to share his insights and experiences about this work. So hope you all enjoy today's session and take away something useful. So okay, now let's give the floor to Xiangrui for the presentation.
Thank you, Professor Jiang, for the introduction, and thank you for Zili Zhang for today's sharing. And now I'm going to begin introduce the great work from Zili Zhang. Can everyone see my screen and hear me clearly?
Yes.
Okay, great. Okay, hello everyone. This is Xiangrui Yang from the University of Hong Kong, and today I'm very glad to share Zili's work, DistTrain, addressing model and data heterogeneity with disaggregated training for multimodal large language models.
Are you in Hong Kong? Are you in Hong Kong now?
You can treat me like I'm in Hong Kong because I'm just next to Hong Kong. I'm in Shenzhen right now.
Okay.
Recently, we can see the multimodal LLM is becoming an exciting AI paradigm. On the left, we see a unimodal LLM, primarily interacting with text. Its capability are largely confined to processing natural language and generating codes. However, the right side introduces the exciting leap to multimodal LLMs. These models can seamlessly integrate its different modalities, not just natural languages and code, but also understanding and generating from photos, charts, and even processing speech and music. This expansion into multiple things allows for a much more comprehensive understanding of the world, enabling applications like robotics and healthcare. And this slide breaks down the typical architecture of multimodal LLM, which can be understood as a three-stage process. First, multimodal inputs like text, images, and audios are fed into a modality encoder. For example, a vision transformer, or a VIT for short. And this module process images, Second, the crucial output of this stage is unified interleaved sequences, where all different modalities are converted into a common representation, a sequence of embeddings. This sequence is then passed to the LLM backbone. Here is a powerful model like GPT or Chen or Llama perform coarse model reasoning, analyzing relationship and the context between different types of information. Finally, based on this reasoning, a modality generator, such as a diffusion model, produces the desired multimodal output, which could be text, a newly generated image, or even audios. However, training such multimodal LLM suffer from two problems: model and data heterogeneity. First, we will introduce the model heterogeneity and how it affects training efficiency. Multimodal LLM is a composite of fundamental different architecture. For instance, the modality encoder, often a VIT, is a relatively lightweight transformer with a small hidden dimension. In contrast, the LLM backbone like GPT, it's a very heavyweight autoregressive transformer, often orders of magnitude larger and more complex. And finally, the modality generator is often a complete different architecture, like conventional unit. The key takeaway here is that these components have different designs and computational needs, which leads to different computational time and pipeline parallelism. And we call this phenomenon model heterogeneity. To take this problem more concrete, this slide shows the actual forward time for the three modules, as shown in the figure. Of 70 billion parameter Llama model, a VIT encoder, and a stable diffusion generator have vastly different computational costs, but crucially, the bottleneck isn't fixed. The first scenario on the left, we are processing lower resolution image. The LLM backbone is clearly the pipeline struggler, which creates pipeline bubbles. And on the right, we can see that in the second scenario, if we switch to generating high-resolution images, the workload shifts dramatically. Now, the stable diffusion generator becomes the struggler, and the LLM and the encoder are often ones waiting. So this model heterogeneity incurs inefficient pipeline bubbles. Now let's turn to the second challenge, data heterogeneity. The slides show the example of a multimodal interaction. The user provides a single prompt that contains multiple tasks. The first is that the user asks what is a landmark, and the second is that it asks the model to remove the plants. One task, and to handle this. The standard training approach is to flatten everything into one long training sequence, as you can see on the right. In the sequence, the different modality tokens are interleaved. The problem here is that this one-size-fits-all sequence comprises distinct and long-tail multimodal data. And this will conduct data characterization. These plots shows the distribution of data size within a typical multimodal training, crops from lion. As you can see, the first and the second chart, the distribution for text image sequences is highly skewed. The vast majority are very short, which is shown on the left part, and the majority are and the minority are very long. The chart on the right shows a single 8K token training sequence may comprise many image subsequences. This distribution is also long tail. Such long tail interleaved training sequence leads to training efficiency since one fixed length sequence with more image tokens may incur more computation in modality encoder. This data heterogeneity leads to two distinct types of performance bottlenecks in parallel training. First, we can see on the left, we see intra micro benchmark struggler problems. In an ideal data parallel setup, each DP worker processes a data sample of the same size and finishes at the same time. However, if data sample 1 and 2 have more image tokens, DP worker 1 inevitably get larger workloads. As a result, DP1 becomes the struggler and blocks the entire training. Second, on the right, this issue extends to pipeline parallelism, creating micro batch struggler. In ideal case, each micro batch has the same computation loads. However, with data heterogeneity, micro batch A might be image heavy. Such heavy micro batch becomes a struggler and prolongs the pipeline warm-up time. Based on the challenges of model and data heterogeneity, we have discussed these slides outline the core design of this solution, DistTrain. To solve this challenge, model heterogeneity, DistTrain introduces disaggregated model orchestration, which means it stopped treating model as a single unit. Instead, DistTrain assigned customized independent parallelism strategies to each distinct module to best suit their unique computational profiles. To do this systematically, it developed optimized formulation that automatically derives the most efficient parallelism configuration, ensuring the workload is balanced. To solve the second challenge, data heterogeneity, DistTrain deploy disaggregated data processing. It uses micro batch reordering to strategically rearrange the data samples distributed across data parallel workers, which balanced the workload and mitigate the struggler problem. Then DistTrain uses inter-microbatch reordering to smooth out the flow of data within the pipeline, which minimizes the pipeline bubbles. Together, these two strategies allow DistTrain to adapt to diverse and dynamic nature of multimodal training data. Now let's dive deeper into how to solve the model heterogeneity as we mentioned just now. The core issue with the standard approach is that a monolithic orchestration, where a single parallelism strategy is applied to the entire model. This creates severe performance imbalances. On the left, you can see this typical setup where data, pipeline, and tensor parallelism are applied uniformly across encoder, LLM, and generator. This strategy completely ignores that there are architecturally distinct modules with very different computational needs. The consequences are shown clearly in the performance chart on the right. This forces the faster components to sit idle, waiting for slowest one in the pipeline. To address this, the solution disaggregated orchestration, which is designed to dynamically balance the computational loads. As you can see on this slide, DistTrain treat each module as an independent unit and assign a customized parallelism strategy. In the top scenario, where the model is processing smaller image, we know the llama backbone is the bottleneck. Therefore, DistTrain allocates more GPU to LLM, speeding up its computation. Conversely, in the bottom scenario, with high resolution images, the VIT and stable diffusion become the struggler. So this workload, the DistTrain dynamically reallocated more GPU to them. The result shown on the chart is that the forward pass time for all three modules become nearly equal in both scenarios. This eliminates the pipeline bubbles and maximizes the hardware utilization. However, this raises a critical question: how do we automatically and optimally decide the disaggregated parallelism strategy? As we just said in the top and the bottom scenarios. To determine the optimum parallelism strategy, we first need to mathematically model the total execution time. This work breaks down the training process for a batch into two distinct phases, as illustrated in the pipeline diagram: the warm-up phase and the steady phase. In the warm-up phase, T warm-up is the latency for the first micro batch to complete its journey through all strategy of pipeline. As the first equation shows, this is simply the sum of the computation time for the encoder, the LLM, and the generator. Once the pipeline is full, we enter the steady stage. The performance here, T steady, is dedicated entirely by the slowest stage, the bottleneck, as captured by the max function in the second equation. The slowest stage defined the clock speed for the remainder of the batch. Based on these two questions, the work formulates optimization problem and solve it with off-the-sheet solver. And it's worth noting that the T steady stage is the main factor that we take consideration, because the T warm up is relatively small compared to the whole process. Now let's turn to how to solve the data heterogeneity problem, starting with the intra-micro batch straggler. To prevent some data parallel worker from getting unfairly heavy loads, it used dynamically scheduling technique called intra-batch reordering. The process, as illustrated on this slide, is straightforward but highly efficient. First, before distributing the data for a global batch, it takes all individual data sample and sort them in descending order based on their computational cost. Then this sorted list, for this sorted list, DistTrain assign each sample to the data parallel worker that currently has the lowest accumulated workloads. And this process is shown on the right part of the slides, and we can see how DistTrain traverse the data sample. For example, it takes 2 to the DP1 and it takes 4 to the assigned 4 to the DP2. This greedily approach ensures that the total computational loads across all DP instances is almost balanced. This simple reordering minimizes idle time, effectively eliminates the straggler problem. To tackle the inter-microbatch straggler issue within the pipeline, DistTrain introduced another scheduling strategy called inter-microbatch reordering. As the diagram illustrates, a pipeline has a warm-up phase, a steady stage phase, and a cooldown phase. The reordering algorithm schedules the minimal micro batches, the fastest one to compute, and at the very beginning and the end of a batch. This allowed the pipeline to fill up the drain as quickly as possible. Conversely, the straggler microbatch are deliberately placed within the pipeline intervals in the middle. This scheduling prevents the straggler from unnecessarily prolonging the warm-up or cooldown period, effectively minimize the pipeline bubbles. To be honest, I think this strategy is quite complicated. To put it simply, is that we just DistTrain just put the small micro batch at the beginning and at the end, and put the big one on the middle. And I think this summarizes this strategy clearly. And this slide shows the workflow of DistTrain. Before launching DistTrain, the program collects the history execution data to build the profiler. The DistTrain manager provides the model cost and solve a convex optimization problem to mathematically determine the best GPU allocation for each module. When user give the number of GPU and batch size, DistTrain automatically decides the parallelism strategy according to the profiled results. Next, the initializer executes this plan that the manager just planned. Unlike monolithic setup, it initialized the encoder, backbone, and generator as 3 independent parallelism units, each with its own communication groups. To mitigate the overhead of tensor parallelism, DistTrain develops StepCCL, a specialized communication library on top of Megatron. Unlike a standard NCCL, which occupies the GPU cores, StepCCL leverages the DMA engine for communication, leaving SM completely free for computation. As shown on the left, StepCCL split large general matrix multiplication into multiple chunks. This fine-grained pipelining allows us to hide the communication overhead behind the computation, significantly reduce the iteration time. However, chunking alerts the data order. So as shown on the right, StepCCL introduced a lightweight layout remapping operation to reconstruct the output. This ensured bitwise correctness with negligible overhead. To evaluate DistTrain, this work conducts evaluation using a large-scale production level setup. The experiments run on a substantial hardware cluster consisting of thousands of GPU interconnected with high-performance network utilizing both NVLink and DRAM and RDMA. For training data, it uses a production dataset from Lion. This work combines the Llama 3 backbone with a VIT encoder and a stable diffusion generator as the training model. In the large-scale experiments, it compares DistTrain to Megatron with monolithic data training approach. DistTrain outperformed Megatron by up to 2 times on training throughput and achieve 45% MFU. For ablation study, it used 96 GPU to evaluate the effectiveness of a disaggregated model orchestration. It chose Megatron as the first baseline, which represent standard monolithic orchestration, where a single uniform parallelism strategy is applied to the entire model. The second baseline is DistMM. This employs a more advanced heuristic-based approach, determining its parallelism strategy from static metrics like model size and flops. As the figure shows, the DistTrain outperformed all the baselines in all setups. To evaluate the effectiveness of disaggregated data processing, it used Megatron as a random real order data loader as baseline. The results show that DistTrain achieved 3% to 11% performance gain. Finally, to conclude the DistTrain, this work demonstrated that large-scale multimodal LLM training is fundamentally hindered by dual challenges of model and data heterogeneity. To solve this paper introduces DistTrain, a novel training system built on 2 core techniques: disaggregated model orchestration and disaggregated data processing. And in the performance side, DistTrain outperformed Megatron M by 2 times and achieved a MFU of 55%. And I think that's all for the presentation from my side.
Okay, cool, wonderful. Thanks for the great presentation. So now let's just move to the discussion part. Yeah, we're very happy to have the first author Zili Zhang here to discuss this work. So does anybody online have questions? You can just unmute and say it, or just type it in the chat box. Okay. Now let me just take as a warm-up question. So Zili, what contributes the most for the best benefits?
I think it's the disaggregated model orchestration. Yeah, it eliminates the pipeline bubbles, which is the first technique.
I think it's this slide.
Yeah. So actually, the disaggregation model orchestration disaggregate the encoder and LLM backbone and generator, and different parallelism can leverages the GPUs as much as possible. And so, for example, the encoder may not require a large TP size, but for LLM, which is a very heavyweight transformer, it requires a much more bigger TP size. For example, 8, even 16. This is the first benefit, and the second benefit is the pipeline bubbles, which is introduced by the model heterogeneity. So, adjusting the different computation time between the different pipeline stages can eliminate the pipeline bubbles, and this is the second benefit. So I think this, the combination of these two benefits is the most contributes the most to the overall benefit.
Okay, I see. Following these questions, in terms of reducing the pipeline bubble, I know that there is a very general solution, in which the stage will be cut into equal length sub pipeline, equal length sub pipeline. So we can eliminate the bubble in pipeline parallelism. So in your design, you didn't choose this kind of solution, right? So
yeah. I think in production it's very hard to cut the LLM in very fine-grained stages. For example, if you have LLM with 20 layers, and the your solution is to cut them in 25, 4, and 10 stages. So if you have for example, you have nine computation cost than one LLM layer. So nine is cannot be divided by 20. So in production, you may not you can't find the actual pipeline size for the training scenario.
Okay, I see. So I understand that there will be some problem, but do you think it is solvable or?
I think in some scenarios, if you design the models, for example, you can contact the algorithm group and redesign the models, and redesign the encoder and redesign the generator. I think it is solvable. But for the most of the time, as a system designer, you cannot define the workload.
Okay, I see. Thank you. So in terms of the disaggregation, I know that there are many system work that adopts disaggregation concept, right? So do you think which is the best scenario that we can use disaggregation to improve the resource utilization or improve the overall system efficiency?
In my opinion, I think if some workload has has dynamic and different computation categorization, for example, this the SOSP, which is PD disaggregation, disaggregated prefill and decoding. Because prefill is computer intensive and decode is memory intensive. So I think in my paper, I call it model heterogeneity and data heterogeneity. Actually, just the overall workload has some different sub workload, and different sub workloads may have different computation characteristics. So I think if you have one workload with some which is consists of many sub workloads, and each of the sub workload is different, so I think it's the best scenario to use the disaggregation approach.
So, following this question, you mean if the workload utilizes many heterogeneous resources, and in some scenarios the bottleneck resource is, for example, the CPU or GPU, and in other scenarios the bottleneck resource is the memory. So there may be some room for us to disaggregate to cut the workload into two parts, right? So they can definitely scale the resources, right?
Yeah.
Okay, cool. I know prefill and decoding utilizes this technique, right? And your previous work dist-serve, right? If my understanding is right. Okay. There is another question from the chat box. So let me just read it. Would DistTrain's performance be affected by newly proposed topology for LLMCs? How about superpod?
I think superpod is a very new hardware. And I think building infrastructure on superpod is very challenging. If you use superpod to train the LLMs, especially multimodal LLMs, you have a node with many GPUs and the bandwidth is very high. I think Metron may not be the best solution. For example, in many scenarios, users, especially the algorithm users, may leverage FSDP, another torch training framework. It's very developer friendly for some developers which may not familiar with the pipeline parallelism, tensor parallelism, and many parallelism strategies. So I think leveraging FSDP and Metron as some design methods in Metron may be the future direction in training LLMs in superpod.
Hi, Cho. Does Zili answer your question? Okay, cool. Okay, any other questions? Okay. In terms of superpod, yeah. Do you think we need another abstraction, a new abstraction for the superpod, so that we can utilize the disaggregated GPU resources and the memory in the superpod to train the multimodal large language models, multimodal large language models. Yeah. So what would be if yes, what would be the best abstraction in your opinion?
I think the abstraction may be the similar, but the actual implementation may be different. I think in production lab or in production, the encoder and generator may be changed by time, because the designer, the algorithm designer have different opinions. But for the AI backbone, which is most time is static, so I think for the encoder, LLM generator, the abstraction may be similar, but for the actual implementation, the encoder may be implemented and the encoder and generator may be implemented by by the developers, especially the algorithm developers, which may be not by system designers. So you can write your code, write the encoder code and generator code in Torch, and train the encoder and generator with Torch FSDP, and leverage the FSDP and integrated the FSDP into the Vectron LLM pipeline, and you can reduce the developer's cost. This is very important in the developer in the production, because sometimes the algorithm designers and the system designers may have some diverse. So I think the abstraction may be the similar. The encoder and LLM generator, the different parts should be different. You should use different resources and should use different algorithm strategies. But the actual implementations could be different. So in DistTrain, the encoder is still writing to the Vectron LLM, and the generator is also integrating to the Vectron LLM. So for algorithm designers, writing the code into Vectron LLM is not very simple. So I think the abstraction may be similar, but the actual implementation could be different.
Yeah, that makes me think a lot. Actually, do you think under this kind of abstraction, for the operators, we always need to coordinate the underlying resources based on the algorithm, right? The apnea or algorithm. So under this kind of abstraction, we need a coordinator or orchestrator to for example, allocate the GPU resources and memory resources to support the model training. So in your experiment, you utilize for over 1,000 GPUs, but actually for a general training task, how can we decide how many GPUs or memory we need to train this kind of model?
Actually, in my experience in production, it's not decided by myself. It is decided by many teams, and maybe in someday a lot of GPUs is available, and I have my task, and I can run my tasks on those GPUs. And maybe the GPUs, maybe the number is maybe 500, maybe 1,000, and maybe 2,000. But whatever, I have to utilize all of the GPUs. So the total number is maybe is not decided by the developer. It is decided by many conditions. But the resource allocation can be carefully designed.
Yeah, so will it be possible to design such a coordinator or orchestrator under this kind of abstraction, so we can better utilize the resources in the cluster?
Yeah.
But for different training tasks, here you target on the multimodal training task, multimodal LLM training task. So if there is any other kinds of training tasks, heterogeneous training tasks, so will do you think will the orchestration be different? Yeah, well, what is
Of course.
What is the key challenges do you think it is in this orchestrator?
So the problem is, how do you design a general orchestrator for many kinds of training workload?
Yeah.
I think the most challenge
the resources in the cluster.
Some work are dedicated to solve this problem. For example, OPA and OpenSURF, it leverage many abstraction like operator and compiler to automatically design the parallelism strategy according to the model architecture and the underlying topology of the clusters and number of the GPUs. However, I think if you have a very large task, for example, LLM training, I think the best way may not be leverage this automatic orchestrator. I think design your own orchestrator is the most efficient solution. So maybe the general one maybe not exist.
Okay, I see. So here you actually use offline profiling to decide how many GPUs are used for different for example for encoder and the other two components, right? So actually you have a controller to decide the GPU allocation, right? So I think this actually is the orchestrator in this serve. Yeah, so that's just these three components are heterogeneous, right? So if we target many other heterogeneous training tasks, I think the thing may be the same, right? Yeah, what do you think?
Not actually the same, but in for example, in MOE training, you should use expert parallelism to train the LLM. And due to the data heterogeneity, in MOE there also exists data heterogeneity because different token may be routed to different experts, and there exists hot expert and cold experts, which incurs the load imbalance. So in such scenario, there also exists data heterogeneity. Their actually solution maybe you may have heard the DeepSeek's EBLB and recently they published the LPLB. So they're targeted in this scenario. The LLM may be constructed in homogeneous transformers, and they may not exist model heterogeneity, but there exists data heterogeneity. So in their task, their solution is to use some algorithm to redesign the token dispatching strategy, or maybe use some reordering in the data set to load the balance. So in this scenario, I think calling it orchestrator may be not appropriate. So I think it may be a more sophisticated scenario. Maybe call it load balancer or just data reordering. So I think the orchestrator is
Okay. So it is actually very difficult to design such orchestrator for heterogeneous training tasks. Okay, so there is another question from the chat box. Let me read it. In DistTrain's disaggregated design, where multimodal model training and data processing are orchestrated separately, have you considered the communication performance implications of operating across a hybrid scale-up and scale-out environment? And how does this heterogeneity in communication domains influence your system's design choices for data placement, scheduling, and end-to-end pipeline efficiency?
Actually, we actually face some data communication bottleneck. You can through the PPT before. No. Maybe in the 10 number 10 page.
Okay.
Yeah, you can see there exist some projectors or the collectors between the modality encoder and their backbone. When you use different parallelisms, the numbers of the projectors and the location of the projectors maybe the problem to solve. If you just use one projectors and put it in one node, which is a centric design, and all of the communication will be passed into the one projector, so maybe the computation bottleneck. So in our design, we place the projectors, just scale the projectors as the scale of the clusters. So you can put the projectors into one GPUs of the modality encoder or on the one GPUs in the backbone, and the number of projectors can scale up. So in the scale up problem, the projectors communication may be the problem. So how to decide the numbers of the projectors and how to place the projectors may be one actual problem.
Hi, hold on. Does Zili answer your question?
Yes, thank you.
Okay, so in your next step, in DistTrain's next level, would you consider the hybrid scale up and scale out environment?
Actually, I'm not thinking much about the next step.
Okay. Okay. Let's just move to the DistTrain's design. I actually have one or two questions. The first question is about the reordering. So does the data reordering affect the final training accuracy?
Actually, not. The data reordering is a reordering within one global batch size. So for one global size, especially in pipeline parallelism, the gradient is accumulated. So which is identical to the scenario which is not reordering. So reordering within one global batch size is accuracy free. Yeah, I think.
And so here your design is design scope is the intra micro batch reordering. And I noticed that there is another reordering inter micro batch, right? Yeah, inter micro batch. So you mean inside one batch, right? Inside just one batch, the data reordering will not affect the final accuracy. But
yeah.
But if we consider the data reordering across batches, will the
of course, they will affect the training semantics. Maybe it will not affect the accuracy, but it actually breaks up the training semantics. In many works, there exists some designs. I think in Aaron Packer, it's a IO system paper. It reorders the data in very long period, and it puts the long tail sequences in very later and just process the short sequences in the beginning. So in such scenario, in the IO systems, this design eliminates the long tail problem. So maybe in other systems there exist some designs, but in this DistTrain, we do not break the training semantics.
Okay, I see. Does DistTrain consider some fault tolerance cases in its setting? Fault tolerance, for example, if there is some GPU failure.
There are many papers about fault tolerance. So in the production, we just leverage the checkpointing, the basic fault tolerance method, checkpointing.
Yeah.
So when some
yeah, I'm just curious about will it be possible to design a co-design approach for the fault tolerance specifically for the multimodal large language model training?
I actually think about this problem. Consider this problem, especially in the superpose scenario. There may be some redundant GPUs just put there and may not be leverages, and the NVIDIA design is for fault tolerance. And in such scenario, we may LLM backbone may be not influenced, but for generator and encoder, we can put more GPUs. Leverage all the GPUs inside the encoder. Once one GPU fail, we just kill one encoder DP worker or kill one generator DP worker. And since the encoder and generator is small, and then the DP worker maybe just the contents of several GPUs, so which is a lightweight operation. So I think this is maybe a possible design choice for fault tolerance.
Yeah.
I have a question. Does Gemini 3.0 address this issue?
Sorry?
The Gemini 3.0. Does it address?
3.0.
Yeah, Gemini, the new release, addresses this issue? Or you haven't tested it yet? Have you used the Gemini 3.0?
No.
For multimodal stuff? Okay, that's fine. So you haven't, no problem. Thank you very much.
Okay.
Well, I have a problem. I think like in the DistTrain, many designs are not to multimodal LLM only. You can use the design in LLM or in LLM training, and you can still achieve some. I think you can still achieve some gains. Have you like tested? Like maybe we will only implement the steps here or some of the DistTrain designs on training only LLM. Will there be any gains?
Sure. The experiments of step call, which is step 0, actually is listed in the paper's appendix. If you are interested, you can check it. Yeah. For other techniques, I think there also exist benefits. For example, the pipeline optimization. Actually, in LLM, due to the packing solution of that, due to the packing method of the data and the attentions computation, so there also exists the data heterogeneity. So maybe if you just leverage the intermag reordering, maybe you can get some benefits.
Yeah. That's what I feel like in reading the first few designs, especially for like the data heterogeneity. I think maybe in real production, like in your collaborators' company, I think they did implement some designs in training LM only model, like maybe so like except from the step CCL, will other techniques like improve the throughput? Like, can you give us maybe some numbers?
We actually haven't checked the takes the experiment. So the actual number, I can't give you the number, but
Okay.
roughly, in LLM training, the problem may be not so severe, but in multimodal training, the problem is very important. So we write a paper to solve it.
Okay, thank you.
Okay. I actually have another question. So here, we're talking a lot of about the training step, right? So how about the fine tuning step? Will the things be different if we conduct fine tuning upon the multimodal large language models?
Maybe in some algorithm design, fine-tuning exists some difference between pre-train, but in most scenarios, SFT is from system perspective, SFT is just a kind of training. Maybe RL system may be different, but fine-tuning in most scenario is the same thing, I think.
Okay. So if you mentioned that for RL there might be some different things. What is that?
I think one important thing is if you generating images or some audios in the generation stage in RL, it's a very different scenario. Since in LLM generation, it's like a prefill, decode. In such scenario, it's maybe a prefill, decode, prefill, decode, which is PD interleaved.
Okay.
It's a very different inference scenario. So if you design an IO system for multimodal training, especially for the generation task, the workload is very different. So I think it's a very
yeah. If my understanding is correct, the design is highly depending on the workload, right?
Yeah.
Okay, got it. So, in terms of the disaggregation, I'm also curious about you have many papers working on disaggregation, right? So if we consider using disaggregation to improve the resource utilization and the overall efficiency, what do you think in general the new problem and trade-offs will be introduced, and how can we in general consider a solution to tackle that?
Maybe first I think there exists one very big problem is the communication. If you disaggregate the workload, you have to do more communication. For example, PD disaggregate the prefill, decode. So when prefill is done, you have to migrate the key cache of the prefill from the prefill instance to the decode instance, and this may encourage more communications. But if you just collocate the prefill and decode, the communication is transmitted by MLink, which is a very high bandwidth. But if you but with the disaggregation, the transmission is through maybe through RDMA, which is somehow low bandwidth. So I think the communication is a very big problem.
Okay.
And for the general design, I think the workload, if you from the system perspective, your workload design, how you design your workload is decide how you design the system. So when we design a system, we have to clarify the workload. So maybe in different nodes, the system design is very different.
Okay, got it. Yeah. Okay. We are around the end of this meeting. Just one last question. For students who are new to this area, what do you think is the best way to get started? For example, to get started into the training optimization or inference optimization, what would be the best way to get started? Yeah, for the new student.
I think the best way is to touch the real production problem. Yeah, I think it is the very.
But actually, it is very to touch the.
It's also the challenge. So since the GPUs are just such a number, and many students are try their best to be a research intern in the company.
Yeah.
So maybe it's a hard step, but I think if you finish this step, you can learn a lot and begin your study. Yeah.
Okay, so how about considering doing research on inference? Yeah, so that we don't have the problem of GPU resources.
Yeah, so other teams and research teams may face the same problem. So in inference area, they are so crowded.
Yeah.
Maybe in the training system, for the training system design, they may have more space to publish their papers, but for inference, you have to try your best.
Okay, got you. Thank you. Okay. Thanks Zili, and thanks Xiangrui. Time is almost up, so we are coming to the end of today's meeting. I would like to give a big thank you to the presenter and the guest speaker for joining us and sharing their experiences. This paper actually brought a lot of interesting points and sparked some great discussions. It definitely gave me a lot to think about. Thank you again for joining today's reading group. And of course, we'd love to see you again in our next SIGCOMM reading group in next 2 weeks. So, all right, that's it for today. And good night and have a good day. See you next time.